This is a calorimetry problem, and we can recognize that because we have two things that are changing temperature. In this one, we have two different water samples. We have a 50-gram sample of water, and we have a 40-gram sample of water. They're mixed, and we're asked to determine what the final temperature is. So I'm going to put a little diagram down here to keep my thinking straight. We start with one temperature bath at 90 degrees C, another temperature bath at 30 degrees C. And our task is to determine what the final temperature is. Now we recognize that there's two changes of temperature. For the hot water bath, our delta T, which is always TF minus TI, is going to be TF minus 90 degrees C. For the water bath, for the cool water bath, our delta T is going to be TF minus a different initial temperature, 30 degrees C. So now we go to the first law, which means our energy is conserved. We have heat lost, or heat gained plus heat lost is equal to 0. The cool water is gaining in temperature, it's gaining heat, and the hot water is losing temperature, losing heat. For each of these situations, we know that heat is going to be equal to the mass times the specific heat capacity times delta T. The difference between these two situations is a difference in mass and a difference in delta T. We can use the specific heat capacity of water either in terms of joules or calories. It doesn't matter. I'm going to choose calories because the numbers are nicer. So for the cool water bath, we have a 50-gram sample. Its heat capacity is 1 calorie per gram degree C. And our delta T is going to be our final temperature, which we don't know, subtracting 30 degrees C. For the hot water bath, its mass is 40 grams. We'll use the same heat capacity because we're still talking about water. And our delta T is TF minus 90 degrees C. And this all sums to 0. Now for this calculation, we're going to have to use the distributive property. So we have 50 times 1 times TF, and from that we'll subtract 50 times 1 times minus 30. Quick reminder, if we use the distributive property, if we have something like 3 times x minus y, that's going to be equal to 3 times x minus 3 times y. Okay, we have this number times the first, this number times the second. So when we do that, we have 50 times 1 times TF, and to that we're going to add 50 times 1 times minus 30. That's minus 1500. So that's on the left-hand side of the equation. Let's look at the hot water bath. So we have 40 times 1 times TF, so that's going to be 40 times TF, and to that we're going to add 40 times 1 times minus 90, which is a negative 3600, and all of this sums to 0. Now the last bit is we're going to be solving this expression for TF. First, we want to collect like terms. So here that's done. We have 50 times TF plus 40 times TF, and we have these two terms here to add together. All right, continuing over here, 50 plus 40 is going to give us a value of 90 times TF, and the 1500 plus 3600 is a 5100, and that's going to sum to 0. So now we're going to add 5100 to each side. So we have 90 times TF is equal to 5100, and finally we can solve for TF. 5100 divided by 90, and that ends up being 56.66 repeating degrees C. For sig figs, we can justify only 2, so we have our final answer of TF is going to be equal to 57 degrees C.